Hi, can you hear me? Hello, everyone. Can you hear me? Okay, so any questions before we start? Okay, so let's see. So you meet. No, you're going to just take the exam on my lab. That's it. Okay, so it's like an assignment that you're going to work on. How many questions? I'm not sure. It's a 50-minute exam. It won't be that long, but they will be like shorter questions. Anything else? So it's 9:40 to 10:30. Okay, so my lab. So what do you mean by open-ended? Like in what sense? Yeah. I mean, most of them will be. Yeah, it will be just like the MyLab stuff. Some things you have to probably do multiple choice. Some things you have to answer with the blanks, fill in the blanks, or type in the answer kind of stuff. No, there's no upload of PDF. It's exactly like your MyLab assignment. Okay. Okay, so let's see. Okay, so I'm going to start the next topic. If you don't have any questions. Okay, so today we're going to do 14.4, first 14.5 and 14.6. Okay, before that, so let's see what we were doing in the last class. So we were discussing derivatives, so partial derivatives. So this is included in your syllabus, so you should already know this. So you should know what a partial derivative is. So dou f over dou s, that means that you take the derivative of this function with respect to s. S is say f is the function of s and so many variables. You take the derivative just with respect to x, assuming that other variables are constant. So just fix every other variable and you think of them as constants and take the derivative with respect to this variable s. So that's what you mean by partial derivative with respect to s, right? So what does it mean geometrically? It means that, so for instance, if you take partial derivative with respect to x, fx is nothing but the derivative of this function, or the rate of change of this function as you move along x-axis. Okay, fx is the rate of change of f as you move along x-axis. Similarly, fy is the rate of change of f as you move along y-axis, and so on. Okay, so that's what you mean by a partial derivative. Okay, so if you're in the plane, you can move along many directions from your point, but if you move along x-axis, the rate of change is fx. If you move along y-axis, the rate of change is fy. Okay, so that's what you have. But just having the derivatives in the x direction and y direction doesn't mean that the function is actually differentiable. So it just tells you the function has nice behavior along x-axis and y-axis, but doesn't tell you anything about a general direction. So if I move in a general direction, what's going to happen? Okay, so the differentiability says that if you move in a general direction, the rate of change, or the change in f, is nothing but the change that you would get by moving just along x plus change you would get just by moving along y. So for instance, if you had to move from this point to this point, so x0, y0, this is delta x and this is delta y. If I want to find how much will I get if I change in this direction of the green line, it's essentially, so to find this change, you can just move the point here and find how much you change, and move from here to here and how much you changed. If you add them together, you get the total change, right? So that's the basic idea. So if you want to get how much the change of the function when you move from here to here, is compute this change and compute this change. So the change when you move along x, by the definition, is nothing but fx delta x, because fx gives you the rate of change. So fx delta x gives you the change as you move from here to here to the delta x distance. Similarly, fy delta y gives you the distance if you move delta y distance along y-axis. So if you add them together, you get the change in f is nothing but fx delta x, fy delta y plus fy delta z. So this is really the main idea. So you should guys, so in general, if you have more variables, you have fz delta z, f, and so on. So so this is the main idea. So this formula is really, really important. So change in f, so it's very easy. So it comes to because of change in x and change in y. Okay, so change x and don't change y. So that will give you the first quantity, and then change y and don't change anything else. That gives you the second quantity, and so on. So this formula is the main idea. So please make sure that you really understand this. Okay, so how do I get the change in f? Is by doing something like this: fx delta x plus fy delta y plus fc delta z. So is this clear for everyone? Okay, so most of today's section will depend on this formula essentially. So for instance, our chain rule, the chain rule is basically take that formula and divide by delta s. If I divide by delta s, I'll get derivative with respect to s is nothing but fx, sorry, this is fx dou x over dou s plus fy dou y over dou s plus fz dou z over dou s. So this is nothing but take that formula and divide by delta s. So this gives you the rate change, and if you want the rate of change, you divide by you can just divide by delta s and take the limit, and that will give you the chain rule. So essentially, this formula captures chain rule, and it gives you so much more. So please make sure that you understand this. Okay. Okay, questions on this? Okay. Change in f is given by, you can compute it in a different way. You just, to find the change in f, you can move along axes and then compute the changes. Okay. First move along x-axis, move along y-axis, and if you also want to move along z-axis, so that gives, just moving along these axes, we can compute the change. Although you might, okay, the actual path you are going, the actual point you might be going is in a different direction. You can reach the direction by moving just along x-axis, just along y-axis, and just along z-axis. Okay, so that's the main idea. Okay, and yeah, the chain rule is this. So use that and divide by delta s, you get this chain rule. Okay, questions? So let me move on to the next. So we'll use this to compute some other kind of ideas. So let's see. So fx is the rate of change of the function along x-axis. Fy is the rate of change of the function along y-axis. So these give you the derivatives along x and y-axis, right? So the question is, what will be the derivative if you move instead of x-axis and y-axis, if I'm moving along some other axis? Say I've moved in the direction of the vector u, what will be the rate of the change? Okay, so instead of moving along x-axis or y-axis, I move along a vector u, what will be the rate of change? Okay, so that's a question. So that rate of change along an arbitrary vector along an arbitrary direction is called the directional derivative. Okay, so you want to understand what is the directional derivative of a function if you move along an arbitrary direction. So what does that mean? So it is denoted by derivative of u, okay, directional derivative of u of f along the direction u is written as duf. Okay, the derivative of f along the u axis. If you move along this vector u, what will be the rate of change? Okay, so the rate of change. So if you try to write that down in the limit definition, the rate of change. So the change as you move along. So if u is u1, u2, so you're moving along u1, u2 axis. So you'll be moving along this point. So from x0, y0, you'll move to x0 plus h u1, y0 plus h u2. So as you move along that line, the difference, the change in f is the numerator, and and the h is in the denominator. Okay, so now you want to understand what this limit is, essentially. Okay, so that's called the directional derivative. Okay, so you're trying to move along a vector, a different direction other than x-axis, and you want to know what is the rate of change. Okay, so again, that's denoted by the symbol duv, and it's physically just you're moving along a different direction, and what is the rate of change of the function. And geometrically, yeah, so what do you mean by the rate of change? Is the slope of a curve, right? The derivative is nothing but the slope of a curve. And what curve are we talking about? So if you draw a plane passing through this, so for instance, if you have a function of f of xy, and so the rate of change as you move along this u direction. So if you move along the u direction, then on the surface you move along some curve, right? If moving along a direction u, we'll be moving along a curve on the surface corresponding to the function, and this rate of change is nothing but the derivative or the slope of that curve at some point that you care about. So okay, it's just the slope. Okay, so that's the notion of directional derivative. So fx is the directional derivative along x-axis, fy is the directional derivative along y-axis. So in general, we want to know what is the derivative along a completely different axis. Okay, so this first expression is the limit definition of the derivative, or you can think of it geometrically. It's like you're trying to find the slope of a curve by moving along some specific directions. If you move along a specific directions, you'll move along a specific curve on the surface of this function. Okay, so please try to, it's always, there are different notions, as I said, so we should try to link all these notions. So one way is to think of as a derivative as the limit, another way to think of derivative as the rate of change, and the way to think of derivative as the slope. Okay, so limit, rate of change, these are all different ways to think of derivatives. So you should be used to like moving in between them. So all of them tell you the same information. Okay, so if I move instead of x and y axis, you can move in an arbitrary axis, and the rate of change along the arbitrary axis is called given any arbitrary axis u is, or the direction u is called the directional derivative. Okay, so let's compute the directional derivative of this function. F of xy, x squared xy, at the point 1, 2 in the direction of u. So can you guys tell me how to compute this? How will I compute the directional derivative of a function f at some point in this direction? So any ideas? Right, so I'm asking you, instead of derivative here, a derivative here, so you want to move along this axis. At this is exactly at 1 over square root 2 is nothing but this is exactly at 45 degrees. Yeah, so just use the limit definition. So so derivative of u along f is nothing but so f of 1 plus, so you're taking the derivative at point 1 comma 2. So f of 1 plus this is u, so 1 over square root 2 h and f of 2 plus 1 over square root 2h. So that is what, if you move from, this is 1 and 2, and this will be, if this distance is h, this will be 1 plus h over square root 2 and 2 plus h over square root 2. So this point is this and this point is 1, 2. So numerator will be this minus f at 1, comma 2. So that is the rate of, that is, so you're moving from 1, 2 to 1 plus h over square root 2 to 2 plus h over square root 2, if you move along that axis. And by h, and you take the limit as h goes to 0. So let's compute that. So just plug everything in. So this f is x squared plus xy. So this is 1 plus h over square root 2 squared plus 1 plus h over square root 2 times 2 plus h over square root 2. So that's x squared plus xy minus x squared plus xy. So minus 1 squared minus 1 times 2 over h as limit h goes to 0. Okay, so that's the limit you're trying to compute. Now just simplify whatever. So can you tell me what you get if you simplify? Just simplify, cancel h, and just tell me the limit. Okay, so I don't have space here, but okay, so just this is some limit that you have to compute. If you compute, it turns out to be 5 over square root 2. Okay, so just compute that limit. So questions? Okay, if I move from a point 1, 2 in the direction of the given direction, so you're moving from 1, 2 to a different point, 1 plus h over square root 2 to 2 plus h over square root 2. So that's why the rate of change would be, yeah, take this value, difference of the value y values, difference of f values, and the difference of x values is h, the distance, you're traveling a distance of h. So that's why that's the limit. Now if you compute the limit as h goes to 0, you'll see the answer. Okay, questions on this? Again, it's nothing but, it's just the derivative when you move along a different direction. So when you move along a different direction, the function is just a fixed, or it's like one variable function, right? It just change, just one variable is changing essentially. Although there are two variables, if you move along one direction, you'll see that the function will be like a one variable function. Right? Because if you move along a fixed direction, there is, like for instance, if you move along x, there's no y dependence. So y is like a fixed number. Similarly, if you move along y, x is a fixed number. But if you move along some other axes, so you'll see that although both x and y are changing, they can't change independently. Well, x depends on y. So that's why it's really a function of one variable if you move along just one axis. Okay. So that's the notion of directional derivative. Okay. So now let's see. So the question is, we have this directional derivative of f along the direction u, and we know the directional derivative along x-axis and y-axis. So it's a function of two variables, and if you know the directional derivative, if you move, so if you know the rate of change along x-axis, rate of change along y-axis, how will you find the rate of change along some other arbitrary axis? The question is, can you write the derivative of some function along an arbitrary axis in terms of the derivative of the function along x and y axis? So the thing is, you can do that. So for that again, so the answer is yes, we can write that. So the derivative along any axis, the directional derivative along any axis can be written in terms of just the directional derivatives along the x and y axis. So how do we do that? So it's basically using this formula again. So this is the main formula. So the change of f can be thought of as, so if you, as I said, the change of f as you move. So you want to find the change of f as you move from here to here is the same thing as change from, you compute the change from here to here and the compute change from here to here. So you, and then you add them up. So in fact, so if you take that limit, and the change is nothing but fx times the change in x-axis times fy times the change along y-axis. Okay, so the change of f will be fx times, so this is hu1, this will be hu2, because this is x0 y0 plus this is this point is x0 plus hu1 plus y0 plus hu2. So the delta f as is the change as you move from this point to this point. Oh, did you get, how did you get rid of h? Oh, so if you simplify this, h will get cancelled. So please try that. So you can see that it will be h, the numerator will come out to be h times 5 over square root 2 plus something. And the limit as h goes to 0, that will be just 5 over square root 2. Okay, just simplify this. This is just this h, just the squares, and just do some algebra, and you will see that the h will get cancelled. Okay. Okay, so again, so just this is the really important idea. Please make sure that you understand it. Okay, I'm repeating it again. So the change in f can be written in terms of change along x-axis plus change along y-axis. If I do that, so and if I take the limit, so you'll see that this derivative along u will be nothing but fx times, say, u1. So u is nothing but fx times, so u is the vector u1 u2. So the derivative will be just nothing but fx times u1 plus fy times u2. Okay, so that's what you get. So if I know the fx and fy and I know the vector u, then I can just compute the derivative along u, the directional derivative along u, by just using this expression fx times u1 plus fy times u2. Okay, so another way to write this is nothing but fxi fyj times this. This looks like the dot product of two vectors, right? So it's the dot product of fxi plus fyj and this vector u1i plus u2j. But u1i plus u2j is nothing but our vector u. This vector fxi plus fyj is called the gradient of f. Okay, so this this vector, the vector which is made of the derivatives of f, is given a name. It's a really one of the most important, probably the most important quantity in the course and in general in mathematics. It's called this vector, which you form by just its components are just the derivatives. Okay, the vector which you form by taking the derivatives as the components is called the gradient of f. Okay, so what this computation tells you is that the derivative of f along any axis can be written in terms of the partial derivatives of along x-axis and y-axis. And another way to say is that if you write those partial derivatives vector as one vector, the formula for the derivative of f along arbitrary axis is nothing but this partial derivative vector dotted with the vector that you care about. So this is what you will get. Okay, the partial derivative vector dotted with the vector you start with will give you the directional derivative along any axis. So if you, so to compute the directional derivative, all you need is to know this this information about the gradient of f. Okay, so again, so let me, so I'm writing it here clearly. So gradient vector is nothing but this vector fxi plus fyj. So basically the components of the vector are just the partial derivatives. So you take the partial derivatives fx and fy, you put them together and write a vector. So that vector is called the gradient of f. So it's written as nabla f. Okay, it's a reversed delta. It's not delta. It's a reversed delta. Okay, so this is a reversed delta. Okay, it's called the gradient of f. Okay, so that's an important quantity. And why do we care about our quantity? As the previous computation that we have done in the previous page tells you that any directional derivative that you want to compute can be written in terms of this vector. So delta f times u. So the gradient f times u dotted with u will give you the directional derivative. Okay, so is that clear? So the directional derivative of any function can be written in terms of, if you know the vector, you can get it just from the information about the partial derivatives. You don't need to compute the limit starting from this limit like previously. If you just compute the partial derivatives, you can compute the directional derivatives. Okay, so let's see this. Let's see an example. Okay, so can you tell me the partial derivatives of f? What is fx? Anyone? Can you guys tell me the partial derivative of f? F is nothing but x times exponential y plus cosine xy. What would be the partial derivative of f along, or fx along x-axis? Guys, yeah, so this is exponential y plus minus y sine xy. Okay, so if you differentiate x exponential y, you get exponential y, and derivative of cosine xy is minus y sine xy. Okay, similarly fy is x exponential y minus x sine xy. Okay, so that is partial derivative. Okay, so now the gradient vector. So the gradient vector I was talking about, this gradient vector is this vector that you get by, so it's fxi plus fyj. That's the gradient vector. Okay, but the point xy is given to be 2, 0. So let's substitute that and compute the vector. So x and y is given to be 2, 0. So if I plug that in, y equals 0 and x equals 2. So this, just plug the values. So this gives you 1 here, and y equals 0, x equals 2. So this gives you 2. Okay, so the gradient vector is nothing but 1 I bar plus 2 j bar. Okay, so that's something that, so if you, just the data of the partial derivative, so you have two numbers, but if you put them together and make a vector out of it, that vector is called a gradient vector. So that's all, there's nothing much. But the nice thing about that vector is that if you want to compute the partial derivative or the derivative of f along some axis, a different axis, you can use this vector to compute the derivative. So if I want to compute the derivative along a vector v of the function f, is nothing but this gradient vector dot this v. So my gradient vector is 1i plus 2j. So if I dot this with this vector that you have, v is given to be 3i minus 4j. If I do the dot product, can you tell me what the answer is? Oh, I just substituted x equals 2 and y equals 0. Just these are the numbers, right? The substitute x equals. So in this expression, substitute x equals 0, y equals 2. sorry, x equals 2, y equals 0. Y equals 0 gives you the second term 0, first term exponential 0 is 1. Similarly, x times exponential y will be just 2. Okay, so this is 3 minus 8, which is minus 5. Okay, so the dot product is minus 5. Okay, so let's see. So that's if I'm just doing it along this vector v, right? So what about instead of the vector v, I try to just do it along the unit vector. So I don't want along a vector v, I want along the direction of v. So what will I do in that case? If I do gradient dot v, you will get this minus 5. That's good. But instead of v, I want in the direction of v. So what will be the vector that will be in the direction of v? Yeah, so divide by the magnitude. Okay, so can you tell me what is the magnitude? So I don't have space here. Maybe I'll do it. So gradient f turned out to be 1, so I plus 2j bar. V was nothing but 3i minus 4j. So typically when you take derivatives, you'd want to take just the direction of it. So you'd want to just compute the direction of it. So the direction of this would be nothing but 3 over 5 minus 4j, 4 over 5j. So this is the vector, but this will be just the direction of that vector. That means it should just give you, it should be a unit vector. So you're dividing by the magnitude. Okay, now so let's say this vector is u. Can you tell me what is derivative along u of f? So it's 1 comma 2 is the gradient of f dot u. So u is nothing but 3 over 5 minus 4 over 5. So what is the answer now? So you have to just divide by 5. Okay, so it will be minus 1. Okay, so is that clear? So there are two things that you need to know again. So this is this quantity is just fx, fy, if you have more quantity, fz and so on. And if you want a directional derivative along a unit vector, u, then it's nothing but this gradient vector times is u. Okay, so these are two important properties. So you are caring about this. So you have partial derivatives, but you're writing, so there's just numbers, but you're writing those numbers as just one vector. You're putting those numbers and writing it as a vector because using that we can compute the directional derivatives. Okay, so again, so let me say it quickly. So same information. So the gradient is this vector. So if you have f of function of two variables, f of x, y, you take the derivative along x and derivative along y, you form that vector that's called the gradient of f. Similarly, if you have three variables x, y, and z, you form fx, fy, fz and write the vector. That vector is called the gradient of f. Is the notion of gradient clear? It's just the partial derivatives. Just take all the partial derivatives and put them into one vector. So any questions on what a gradient is? As I said, this is one of the most important ideas in the whole course. Okay, what a gradient is and what is it telling you? What is the meaning of gradient? How to manipulate everything about gradients. Okay, so please make sure that you understand this. Okay. Yeah, question? Okay, so what are some properties of the gradient, right? If I want to do something like gradient of f plus g, if you have two functions, how do I compute the gradient? So it's not simple. The gradient is like just like the derivative. Okay, so when you think, so gradient is this is a vector, right? It's not just a number, but it's a vector which kind of derivatives. But the way you would want to come, so but it has algebraically there's no difference between derivative and gradient in the sense that, so the gradient of sum of two functions is nothing but you can just, it's like differentiating two functions is differentiate the first and differentiate the second. If you want to differentiate the difference, is differentiate first and subtract the derivative of the second. If you want to differentiate first function times some constant, you can pull out that constant, right? And similarly, product rule. If you want to differentiate the product of two functions, is like first function times the derivative of the second, second function times the derivative of the first, right? This is like the normal product rule of the derivative. Similarly, if you want to differentiate the ratio of two functions, it's the quotient rule. The denominator squared times denominator times the derivative of the numerator minus numerator times the derivative of the denominator. So that gives you the quotient rule. But the only difference is, so it's completely similar to the derivative, but the only difference is that delta f is not a number, it's a vector. Okay. So the algebra, when you're doing algebra, you're doing any manipulations with this vector, with delta f, this nebula f, the gradient of f, it's exactly similar to differentiate the algebra that you would do with derivatives. Okay. For manipulating any algebraic stuff, the gradient is exactly like a derivative. Okay. So these are, is that clear, everyone? So it just, because it's in fact, right, if you write it in components, it's because delta is nothing but, this nebula is nothing but derivative, it's a list of derivatives, x derivative, y derivative, and z derivative. So along each component, all these formulas are valid, so that's why it's the formulas are valid. Okay, so all these formulas are coming from the formulas for the derivatives themselves. So if you can just please, if you want to, you should verify them. It's the same. So whatever formula you have for the derivative, this nebula or this reverse delta, the gradient of f will have the same formula. Okay, so and oh, I forgot to tell you. So this is okay. So the symbol is in, if you want to type, is called nebula. If you, people call it del. If you or the gradient. Okay, so you can, these are what you want to call them instead of okay. These are different ways to call the symbol. So it's del f or nebula f or gradient f. You can call them with any of these names. Okay, so okay, so I'll be using them into, like, I'll, depending on my context, I'll just use either del f or gradient f or nebula f. So all of them will tell you, are basically talking about the symbol. It's a reversed delta. It's not delta, it's a reversed delta. Okay. So, okay, so gradient is this list of numbers, fx, fy, fz, you just compute the partial derivatives. But what does it mean? So you're writing a vector corresponding to the gradient, but what does gradient give you? So what is, so this is the previous list of things is just how to do algebra with the gradient, in fact, but why do we care about gradient and what is the geometric meaning of the gradient? So let's see. As we said, the first thing is that the directional derivative of any function is the dot product of the gradient and that vector. Okay, so that's the main formula. So the gradient dotted with a vector, unit vector, will give you the directional derivative. Okay, that's why we care about the gradient. So if you dot with that vector with the unit vector that you care about, it will give you the directional derivative. Okay, so let's see. So it's the dot product. That means the dot product of two vectors is nothing but the magnitude of the vector times cosine theta. But u is of, say, in this case, of magnitude 1. That means this is delta f times cosine theta. Okay, so you can see that the magnitude, or you can see that the dot product, which is the directional derivative of f, is the magnitude of the gradient vector times cosine theta. So that's something that is important about the gradient. So the gradient is just the list of these numbers fx, fy, fz, but it tells you it's related to these directional derivatives. Okay, so from this the question is, so imagine that you are at a point and you are moving in different directions. You can move in different directions. Oh, I mean, okay, I'm just taking u to be magnitude 1. Typically when you take, so you only take derivatives along. So when you write du, you typically write du for u of magnitude 1. Okay, you only care of the direction. You want to talk about the direction of the derivative. I mean, derivative along some direction instead of the vector. Okay. Is it clear? So so this is called the directional derivative. So you want just the derivative along some direction. So if you move along this direction, what is the derivative? Okay, so u typically just represents a direction, so which it doesn't really have a magnitude. So it means it has magnitude 1. Okay, so the question is, if f, so at any point in the plane, right? You are in the plane, say, or in, so you can move in different directions. So the question I'm asking you is, in which, so given what is the direction in which you should move so that you'll get the maximum amount of derivative, or the maximum change, or maximum rate of change? Can you guys tell me what is the direction in which you'll get the maximum change? No, right? So let's see. Yeah, so it happens if theta equals 0, right? So the directional derivative of f, it means that the theta equal to 0, right? This is delta f times cosine theta, and theta can be any number. So that means theta equals to 0. Okay, so what does theta equal to 0 mean? Theta is the angle between gradient f and your vector u, right? Theta is this, in this case, is the angle between the gradient vector and your unit vector u. And you're saying that angle theta is 0. So what does that mean? Right? So this quantity grade del f times cosine theta is maximum. You can get the maximum derivative if you make theta equals 0. So, and theta equals 0 means that your u is essentially along the direction of the gradient. Okay. So that's what. So this is what I've written here. So this is called the steepest ascent. Okay. So the gradient basically is the direction of the steepest ascent. So that means that at any point in the space, if you move along the direction of f, if your vector u that you're moving is along the gradient vector, that means you're moving the most. Like you have the most rapid increase. The directional derivative will be the highest. But if you move opposite to the vector, the cosine, that means theta is pi, so it will be negative. So the derivative will be the most, it will decrease the most if you move opposite to the vector. And if you move in a perpendicular direction to the vector, that means cosine theta is 0. That means you'll get the derivative is 0. Okay. So those are, so from this you'll see the 3 cases. So what I'm saying is that, so imagine that you are at some point and you know the gradient vector. So this is the gradient vector. And so for you to get the maximum amount of change in your function, you have to move along the gradient vector. If you move along opposite to the vector, you'll get the maximum decrease. And similarly, if you move perpendicular to the vector, the function won't change. Okay, so that's what you mean by the steepest ascent. So if you move along the direction of the direction of the gradient, you will have the maximum amount of change in your function. Okay, so how is that useful practically? So for instance, so imagine that f is the height of some hill, right? If your surface that the function is, say, is the height of, so there's some terrain and there's like some shape that you see, f represents, so if you have some shape, f represents this the height of the surface at some point. Then you are, so the question is, so you're trying to ascend, say you're trying to move up this cliff, for instance, and you're at some point. You want to ask what is the direction in which you move so that you'll go up faster, right? So what direction should you move? So this is some surface. So what is the direction in which you move so that you will get the maximum derivative? That means you will be able to get the maximum height. So so you can choose to move along different directions, right? What is your choice of direction so that you'll be able to move higher, like in the fastest time? So at each point, the direction that you need to move so that you will get to a bigger height faster is the direction of the gradient. So the clear, if f is the height of the hill or the cliffs or the terrain that you're trying to move on. So you should move along the direction of the gradient vector. Okay, so this is really important. So gradient helps you to, so that all these ways of thinking about gradient. So it's a vector defined by the partial derivatives, but the important thing is that along the gradient direction, the function will increase the most. And along the direction which are perpendicular to the function, this gradient, the function won't change at all. Okay, so what does that mean? The function, so if this is a gradient vector that you have, if you move perpendicular to the gradient vector, the function doesn't change. That means that the gradient vector is normal to the level curve. So the level curves are the curve along which the function doesn't change, right? So the level curve is the curve along which the function doesn't change. And you saw that the gradient f is perpendicular to the direction in which the function doesn't change, right? So if any direction along which which is perpendicular to the gradient f means that the derivative is 0 along that direction. So that means the function doesn't change along those directions. So these are the directions along which the function doesn't change. If you move along here, the function doesn't change. So that means along those curves, the function is not changing. So those are the curves along which the value of the function is constant. So such curves are called level curves or the contour curves, right? So that's why if you imagine if you have a function, if you have these contour curves, the gradient f is nothing but the normal at any point. So for instance, here it will be this point. Here it will be some point like this. So the gradient f will be the normal to the level curves. Okay, so that's another way to think of gradient. And the gradient f is a normal to the level curves because along the gradient will give you the direction in which the function has to change. Up and perpendicular to the gradient, the function doesn't change. Is that clear? So geometry of the gradient. So gradient, if you move along the gradient, you will change. The value, the function will change. So for instance, if you move perpendicular to this, so along the gradient, that means that you were moving from one contour to the other contour, right? So for instance, you might be here, then if there's a gradient, you're moving to the next contour. So that means that you're changing, the value of the function is changing. But if you don't, if you're only perpendicular to the vector, then you're basically along the same contour essentially. That means the function is not changing. Okay, so that's why the gradient direction tells you which direction should you move so that the value of the function changes the most. And the direction perpendicular to the gradient will tell you is basically along the direction, it's tangent to the direction of the level curve. So, okay, so if you want to change the function, you have to move along the gradient. If you don't want to change the function, you have to move perpendicular to the gradient. So questions on this? So this is really important. This is the geometry of the gradient. So please make sure that you understand. So these are two numbers, fx and fy, and you draw that vector. But what will that represent geometrically or physically? It gives you the direction in which the function changes the most. And it's basically, another way to think of it is just that it is perpendicular or normal to the level curves. Okay, so these are two different ways to think of it. Okay, the gradient is normal to the level curves, and gradient is basically the direction of the steepest ascent or the steepest increase, the most increase direction. Okay, so let's see, let's compute something. So there's a function fx, y, z, x cubed minus x squared minus z at the point 1, 1, 0. He's asking the derivative of the function in the direction of v. So can you guys tell me what is the derivative of this function and the direction of v? Okay, first to do that, we have to compute the gradient vector. So let's compute the gradient. So fx is, can you tell me what fx is? Just 3x squared minus y squared. So which is 3. Fy is minus 2xy, which is minus 2. And similarly, fz is nothing but minus 1. So if I put in all this information together, you see that the gradient f vector is nothing but 3 minus 2, 1, minus 1. This is the gradient vector. So, and the direction of v, so v is given by this vector. Can you tell me the direction of the vector v? What will be the direction of the vector v? Oh, 3 minus 1 is just 2. Good. This is 2. So, and the direction of the vector u. So what, can you tell me what is the direction of the vector u? So v is given by 2, minus 3 and 6. So the direction would be just v over the magnitude, which is 2 minus 3, 6 is the vector, and you have to divide by the magnitude, which is 2 squared plus 3 squared plus 6 squared. And this is 7, so this so the vector basically is, the denominator is 7. So this is 2 over 7 minus 3 over 7. So minus 2 over 7. What? Oh, minus 3 over 7 and 6 over 7. Okay, so now the derivative along the vector u is nothing but gradient f dot u, which is, just take the dot product of these two vectors, 2, negative 1, dotted with 2 over 7, 3 over 7, and 6 over 7. Okay, so if you compute this, this turns out to be, so just 4 plus 6 minus 6 is 4. 4 plus 6 minus 6 is 4, so 4 over 7. Okay, so that's how you compute the directional derivative. So this is nothing different. So you compute the gradient vector, you compute the vector or the direction vector, and you take the dot product. That gives you the directional derivative along the vectors. So the next question is, oh, it's okay. It's increasing at a rate. The derivative is 4 over 7. It's positive, right? So the function is increasing at a rate 4 over 7. Right? It's the same thing. If derivative is positive, that means you are increasing. The function is changing to positive. So it is increasing at a rate of 4 over 7. Is that clear? If I move along the direction, the function is, the rate of change is 4 over 7. But you want to understand what is the rate of, what direction So this might not be the most rapid direction. What is the direction in which it changes the most? So for instance, along the x direction, already we saw that along x direction, the change is, the rate of change is 2. And along y direction, it is decreasing at a rate of 2. Along z direction, it's changing at a rate of -1. So what would be the direction in which it changes the most? Okay, so typically, so we take it to be a unit vector because it's, you just want the direction, the vector derivative along the unit vector, right? We just need the directional derivative. That means what is the derivative as you move along that vector? Okay, so you should, when you ask the derivative along the direction of that vector, you want to just take the unit vector in the direction. Okay. You can always dot it with anything you want, but typically we would just take the directional derivative. When we write directional derivative, we only care about derivative along the unit directions. Okay, so that's why we dot it with the unit directions. Okay, so again, so what is the direction in which it changes the most? As I said, the direction in which it changes the most is the gradient direction. So yeah, it would be the direction of this del f or the nebula f. So it is this. And what is the magnitude of the change? Can you tell me what so how much will be the, so 2 minus 2 minus 1. So gradient f is nothing but 2 minus 2 minus 1. So what is this direction? Can you tell me what is, so what is the magnitude of this? Yeah, it's 2 squared plus 2 squared plus 1, which is nothing but 3. So we see that there's a, if you move along this direction, the change that you will get is 3. So along gradient f, the rate of change is 3 units, is 3. So and in fact this will be the maximum rate of change. Maximum 3 will be the maximum rate of change, because we said it will be magnitude of the gradient of f times cosine theta, and the maximum you can expect is just when cosine theta equals 0. So that's it. So what is the direction? You can write the direction if you want. So it's 2 minus 2 minus 1, right? So the direction is 2 over 3 minus 2 over 3 and minus 1 over 3. So some direction. So along the direction, so along this direction, you have a rate of change of 3. So it means that if you move along the given vector, you'll only get 4 over 7 as the rate of the change. But if I move along this vector, I'll have the maximum rate of change, right? So I can move along x-axis, y-axis, or you can move along z-axis. You can move along that given vector. So right, all I'm computing is the gradient vector, and I'm saying along the gradient vector, you have the maximum rate of change. Right? In the initial, the problem has given you this direction, and along that direction, all you got was a rate of change of 4 over 7. If I move along x-axis, I'll get a rate of change of 2. Moving along y-axis, I'll get a rate of change of -2. Z-axis, I'll get a rate of change of -1. but none of them will give you the maximum rate of the change. You have to move along a specific direction, which is this, the direction of the gradient. If I move along that direction, this direction, the gradient direction, basically, that gives you the maximum rate of change, which is 3. Okay. So again, so the gradient vector helps you to find, so it's some vector in the space. We don't know what it is. It's some vector. If you move along that vector, you'll get the maximum rate of change. So it's basically telling, it is the direction which tells you to, in which you have to move so that you'll change the maximum. If you move along some other directions, you would not move as the direction, what the change won't be that much, right? So that's the physical significance of gradient. Okay, so this is something that, the word gradient is something that you keep on seeing in different contexts, and nowadays in modern world, it's much more important. This artificial intelligence people kind of do this gradient descent. It's one of the most important algorithms to compute anything about in like modern machine learning world. Okay, so gradient descent. So we'll see something about the gradient descent in the class, but it's essentially some understanding this idea that if you want the direction in which you have to move so that you'll get the maximum impact. So for instance, what is the best choice to make, right? You can make different choices. You can move in different directions, but what is the best choice? The best choice would be a choice that moves along this gradient vector so that you'll get the maximum change. So that's why in real life, there are different possible choices to move. You can do different like, so if you're playing a game, you can do, or if a computer has to make a decision, it can make the decisions along different axes or different kinds of decisions. But the best decision would be the decision that moves along this gradient vector. Okay, so that's some information about the gradient vectors. Another information, as I said, the gradient is the direction of the maximum change. But the perpendicular to the gradient means that you are just along the curve. So along the level, the function is constant along that curve, right? So that means the gradient is the normal curve of the level curve at that point. Okay, so the gradient is a normal to the level curves. So we can use this to compute the tangent line to the level curve. So can you tell me how to compute the tangent line to the level curve? I want to compute the equation of this line, the tangent line. I know this direction. I know the gradient vector, and I want to compute this other vector. Can you guys tell me what I need to do? I want to compute the tangent vector. I know this is the gradient vector. I want to compute this tangent. So what property? How do I do that? Right, so let's see. So if this point, I know this point is like say x0, y0, and say this other point is say xy, right? So this vector has to be perpendicular. So the vector that you get by drawing from this point to this xy has to be perpendicular to the gradient, right? So if I draw that, so what does that mean? So this vector x minus x0, y minus y0 is perpendicular to the gradient vector. So the gradient vector is fx, fy. So it's perpendicular, that means the dot product is 0. Okay, so that if I write that down, so x minus x0, y minus y0 is this vector which is along my tangent line, and this is the gradient vector, which is fx, fy. And because they're perpendicular, if you use that information, you'll get that this is the equation. So dot product of those two vectors is 0, is the same thing as fx times x minus gives you this equation. Fx times x minus x0 plus fy times y minus y0 is 0. Okay, so that will help you to write an equation for the tangent. So let's see. So the question is, so there's this curve x squared over 4 plus y squared equals 2, and you want to find the equation of the tangent line. So can you guys tell me how to do that? So this is, yeah, so let's do that. But before, so what is this curve? This would be some curve like this. Okay, and you would want to get the tangent vector at, so this is the line that you want to compute. Okay, so this is some ellipse, and you want to compute this tangent line. So first let's compute the gradient. So f of xy is say x squared over 4 plus y squared. Good. So right, so this ellipse is the curve which is x squared over 4 plus y squared, or you can take minus 2 as well, if it doesn't matter. So this curve is what you have, and it is the level curve for this function x squared over 4 plus y squared, right? An ellipse means that this quantity is constant. Okay, so what is gradient of f? The gradient of f, compute the x derivative, fx, fy is x over 2 and 2y, which is x equals -2, y equals 1. So this is -1 and 2. Okay, so the gradient f is 1, 2. So therefore the equation of tangent would be this. So equation of the tangent is, say this point is given to be -2, 1, and say a random point is x, y. So the equation of tangent would be this x minus -2 and this vector which is y minus 1. So that's a vector which is along the tangent line, is perpendicular to this gradient vector. So that equals 0. So which would be -1 times x plus 2 plus 2 times y minus 1 equals 0. So that's the equation of the tangent line. Okay, you can simplify this if you want. So just bring x's and y's on one side. So this would be x minus 2y equals -4. Okay, x minus, let me erase this. X minus 2y is -4. Okay, is that clear? So if you want to find the equation of the tangent, tangents are perpendicular to the gradients. So compute the gradients and then use the fact that the line is perpendicular to the gradient, then you'll be able to write the equation of the tangent line. Okay. Then there is something called chain rule for paths in your textbook. It's not really different. It's the same thing. So if you want to compute the derivative of a function, which is f of r of t, okay, so a function which depends on r of t, and r of t is a function which is x of t, y of t, and g of t, right? Instead of thinking of f as a function of x, y, and z, you can think of f as a function of x, y, the vector x, y, z, right? previously we are considering f, x, y, z as just a function of three variables, x, y, and z. But you can also think of it as a function of this vector x comma y comma z. So if I do that, and I want to compute the derivative of this function f of r of t with respect to time, and we saw that the chain rule tells you this. The derivative along of this function is nothing but partial derivative with x times the x derivative, partial derivative with y times y derivative, partial derivative times z the z derivative. But if I write it, there's another way to write it. So we can kind of think of the chain rule as basically the first, these derivatives are basically the gradient vector, okay? And then dx over dt, dy over dt, and dz over dt is nothing but the velocity vector. Wait, is my screen sharing? Can you see my screen share or? Okay. So yeah, so the another way to see the chain rule is that, yeah, so you can think of this derivative vector as not, and this chain rule is that the derivative is this gradient vector times dr over dt. Okay, so that means if you differentiate f of r of t, it's nothing but the gradient vector times derivative vector, which is r prime of t. Okay, so what does it mean? So the chain rule that we have seen before can be thought of as just like the chain rule in one variable. But the only difference is that instead of the derivative, we take the gradient. Instead of the normal product, we take the dot product. Okay, so if it's just a function f of some r of t and all of these things are normal one variable functions, we know that derivative of f of r of t is nothing but derivative of f with respect to r times derivative of r, right? So instead of that, I'm saying to compute derivative of f of r of t is nothing but take the gradient vector and times the that's the derivative with respect to r, or this x, y, z, times the derivative of r. So, but the notion of times is the dot product. Instead of derivative, you make it this gradient. Okay, so you can think of the chain rule as just similar to the chain rule for one variable if you interpret all these things like this. Okay, instead of thinking of it as a derivative, think of it as a gradient. And instead of taking the product, you take the dot product. This chain rule above, this is something that you have already seen, will be the same thing as we can see it in terms of this formula, and this formula is exactly kind of similar to the one variable formula. The derivative of f times derivative of r. Okay, so that's called the chain rule along paths. It's not very different. It's the same. If you write it in x, y, z coordinates, it's the same formula that you have seen. But I'm saying you can rewrite that formula in terms of this machinery of gradient. Okay, so that's something about two variables, and similarly you have more information about the gradients. So this is let's say again, even in the case of three variables, f of x, y, z, the gradient gives you the direction of the rapid increase. Okay, there's no difference between two variables and three variables. It's just the gradient always, the direction of the gradient will always gives you the direction of the most increase. But what does it mean in terms of the level curves? So if you have f of x, y, z, we don't have level curves anymore. We'll have level surfaces, and still it is in the normal direction. Okay, so that's the only difference. So the gradient will always give you the direction of most increase, but in case of 2 dimensions, it will be a normal to a curve. In case of 3 dimensions, it will give you normal to a surface. This is some surface, and it will give you the normal direction to the surface. It's perpendicular to the level surface. So that's the whole difference between 2 and 3 dimensions. Instead of a curve, you'll have a level surface. Okay, so why, but how can you use that? Just like we computed equation of the tangent line using the gradient, now you can compute the equation of the tangent plane. Right, because you know the gradient direction, the tangent plane is perpendicular to the gradient direction. So, let's see. So if you take the level surface and the gradient vector will be perpendicular to the surface. Okay, it will be normal to the surface. So if you want to compute the tangent vector, you have to just compute a plane perpendicular to this tangent vector. So the gradient vector is perpendicular to the surface, or the normal to the surface. If you want to compute the tangent plane, just compute a plane perpendicular to this vector. Okay, so this is an example. So this will give you the direction of the gradient. And now if you want to compute the tangent plane at that point, it's the same thing as computing a plane which is perpendicular to this direction. Okay, so we know how to do this. So let's try to do that. So if this surface and I want to compute the tangent plane is essentially given by this normal vector. So we know the normal vector, or the vector perpendicular to the tangent plane. Okay, so let's see this. So you have the surface given above. Okay, if you want. So, and I want to find the tangent plane. So what is the equation of the tangent plane at some point which is 1, 2, 4? Can you guys tell me what I do? What do you need to do to compute the equation of the tangent plane? Okay, as I said, the information is that the gradient vector is perpendicular to the tangent plane. Okay, so first compute the gradient vector. So the gradient vector, so can you tell me what the gradient vector is? F is x squared plus y squared plus z minus 9. So the gradient vector is 2x, 2y, and 1. Okay, so if I substitute x equals 1, 2, and 4, so you'll see this is equal to 2, 4, and 1. So that's the gradient vector. So this vector that we have will be 2, 4, and 1. So from that, can you tell me what would be the tangent plane, the equation of the tangent plane? Right, so any vector on the plane, so this is any vector on the plane will be perpendicular to the normal vector. Right, so that means any vector on the plane is x minus x0. So any vector on the plane would be this. So this is x minus 1, y minus 2, and z minus 4. Right, if the point is x, y, z, and you're starting from 1, 2, and 4. So the vector on the plane will be x minus 1, y minus 2, and z minus 4. So that vector would be perpendicular to this normal vector, 2, 4, and 1. So that's why the dot product would be 0. Okay, so the dot product of the gradient vector and this vector on the plane is 0. So if I compute that, you get 2 times x minus 1 plus 4 times y minus 2 plus 1 times z minus 4 is 0. Okay, so that would be the equation of the tangent plane to the surface at some given point. Okay. So all I'm doing is to compute the gradient vector, and the gradient is perpendicular to the level curves. It's perpendicular to the level surfaces. That will help us compute tangent planes in 3 dimensions, tangent lines in 2 dimensions. Okay. So that's some information about gradients. Okay, again, so this is a really, really important topic. Please make sure that you try to understand different aspects, how to compute the gradient, what is the physical meaning of the gradient, what is the geometric meaning of the gradient, what happens if you move along the direction of the gradient, how is it related to the directional derivatives. Okay, so all these ideas that we have discussed today, please So there are too many of them. So, but it's simple. It's just there's some vector called gradient, and it tells you a lot about the rate of change. It's the best along the direction of the gradient. The rate of change is the maximum. Perpendicular to it, the function is not changing. That means you are along a level surface. Okay. So so I'm done. So we'll continue in the next class. So if you have any questions, you can stay around and ask me. And yeah, so good luck for the exam. Okay, so